Good evening, good evening, good evening everyone. It's 9 o'clock, it's Wednesday night, and that means it's physics night. So tonight we're looking at light, the whole process behind how we get light transferred from one place to another. We're going to look at reflection, we're going to look at refraction, and we're going to look at dispersion. There's a lot to do in 30 minutes, so we're just going to crack on at it. Alright, first of all, light is a wave. It behaves as a wave in most situations, and as a result it can therefore be treated as any other wave. It reflects, it refracts, and it disperses like any other wave. Okay, so let's imagine that we have a ray of light. So we're going to draw a ray of light as a little line with an arrowhead on the end of it. Ideally you would put the arrowhead in the middle if you're doing an exam. And if you're doing an exam, just make it nice and obvious that's a ray of light. It's not a ray of light until it's actually traveling like that. Now, rays of light hit stuff, right? And depending on what they hit, then different things happen to them. But broadly speaking, when a ray of light hits anything, it's going to bounce off it. There's going to be a degree of reflection, even if it hits something that's transparent. Pretty much when light hits anything, there's some degree of bounce back, and we call that bounce back reflection. Okay, and the way it bounces off is entirely predictable. That you've probably experienced this already. When you throw like a ball, a wall, it reflects off. You can predict where it's going to go to. So true is the case with light. So if this light comes in here, you pretty instinctively know it's going to bounce off that way somewhere. And this is where we come to misconception number one about light. That everybody thinks that it's this angle here, let's call this, say, 30 degrees, is going to be equal to this angle here, 30 degrees. Now, in a lot of cases, that actually is true, but it will only be true if this object is flat. Okay, if this object is flat, this will be true. But what happens if we have a randomly curvy object? Let's get the pen out and just draw something completely random like that. There we go. Okay, this diagram is still accurate. The problem is that we have a variety of angles here. We have this angle, and we have this angle that's bigger. Then we have this angle that's different, and then we have this angle. These are all angles that are part of that line, and that can't be allowed to be true. We can't have multiple angles for the same measurement. So we need some standardized way of measuring the angle that light hits stuff so that we can make up some rules around that. We need some normalized rules. That's exactly what we do. We draw something called a normal. So what you have to do is you have to imagine that you zoom right in at this point here. Okay, and let's try and draw that. Okay, so right at that point, if you zoomed right in, you would see just the top edge of this thing and a ray of light coming in like that. Okay, now at the point where the light hits the object, we draw something called a normal line. Okay, and a normal line is a dotted line that is drawn in such a way that it starts where the ray of light hits the object, and it is at 90 degrees, that's a right angle, to the surface that the light hits. Okay, so it doesn't actually matter about where the light is, it actually matters about the surface. Okay, so it's 90 degrees to the actual object, which sort of makes sense, because if you bounce light off a slanty surface, it's going to go somewhere different than if it's off a completely flat surface. So the surface does matter, and this is where you measure from. So we have this kind of straight up and down thing here. Okay, we'll deal with situations where it's not completely flat and straight up and down anyway, a little bit later on. Okay, so then what we've got to do now is we've got to do a little bit of labeling convention. So labeling wise, we call this angle here, this one here, we call this the angle I. Okay, and the reason we call it I is that this is the angle, I equals the angle of incidence. Okay, there's been an incident, okay, therefore we have an angle of incidence. This is the angle of incidence, and therefore this is called the incident ray. Alright, so this is the one that's actually causing the stuff to happen. It comes in. Okay, so a ray bounces off in this case, so and it does so, like we say, in a predictable way. It bounces off over here somewhere. So let me just draw that in, something like that. Now, if you're sitting CA Physics, you don't actually need a protractor in the exam, so judging this by eye is perfectly fine. But you want to do a halfway decent job of it. So you want this ray of light to actually bounce at exactly the same point that strikes there, so there's no random gaps or anything like that. And you want it to look roughly the same way. Okay, good evening JD in the comments. Okay, so we've got this kind of set up here. Now, what we know about reflection is that it is predictable, and this angle here, this angle is called R, and this is the angle of reflection, in a weird turn of physics actually calling something exactly what it is. So R is the angle of reflection. And notice that these angles are being measured from the normal. And importantly, the normal is considered to be the 0 degree line. Okay, so anything that comes in along the normal is called 0 degrees. And then you work around from there. So my angle of incidence would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, all the way around to here. And this is what about, it's about 60 degrees, so maybe 70, something like that. Okay, so if this angle in here is, let's call it 65 degrees for fun. If this angle is 65 degrees, then we can say that this angle in here is 65 degrees also. Okay, and this is called the law of reflection. Okay, the law of reflection is nice and simple. It says, once I get the typing, so the law of reflection is just that the angle of incidence is equal to the angle of reflection, where these angles are being measured from the normal. Jobs are good, and any form of reflection follows that pattern. Okay, now what we're going to do is we're going to use that law to position an object in a mirror. Alright, so let's go and get ourselves a little mirror. So drag one in from here. Okay, this is a mirror, kind of universal symbol for a mirror here. This is the kind of real side of the mirror. So this is reality is out here, and then this is inside the mirror. And what we're going to do is we're going to try our very best to draw a diagram without use of protractors or squared paper and show you how an object is inside the mirror. And we're going to feel really badly at that. And hopefully by feeling really badly at this, I can show you an interesting way to cheat. Okay, so let's put ourselves an object, just a dot. That I'll make it reasonable sized for those of you watching on mobile devices. Hopefully you can see that. All right, so this is an object, and this object can be seen. Okay, it can be seen from any angle, and as a result, that must mean that there's rays of light coming off this object in every conceivable direction. Right? Because if a guy down here can see it, there must be a ray of light coming towards him this way. If a guy over here can see it, over this way. If a girl over here can see it, then there must be a ray this way. And you can't really imagine a place where somebody couldn't see that. So there's rays of lights in all sorts of directions. We're going to pick two. And it doesn't really matter which two, but some are better than others. We're going to pick a ray of light just comes and goes that way. I want to hit the mirror. I'm going to track what happens to that ray of light. Okay, so the instinct that should be in you at the end of this video is as soon as you see a ray of light hit any object of any description, you just automatically draw normal. It should be really, don't even think about it, don't read the question, don't do anything, just draw normal, boom. Okay, this here is, I'm going to do it in red, this is my angle of incidence. My angle of reflection should be roughly the same size. Okay, and you know what, because I'm on a computer, undo that. What I'm going to do is I'm going to copy and paste that so that we can try and make it as accurate as possible. When you're in an exam, just do it the best you can by eye. You'll see that this, even doing this is not ideal. Tilt that a bit, that's still not good. No, we'll not do that. Good enough. Okay, this ray of light is going to bounce off, so we start our ray of light back where it came from, and out it comes. Somewhere along that line. And that would be more than good enough to get the mark. Okay? But this doesn't actually tell me where I see the object. This just tells me where one ray of light goes. And in order to position an object, you need at least two rays of light coming from the same object, giving your brain the same information applying the same information to your brain can then work out, right, that's the same picture, one slightly left of the other, we can use that to position this object. So let's do that. Let's pick another ray of light. It doesn't matter where from or where to. I could go up here if I wanted to, though it's going to be problematic because I don't have enough page. So I'm just going to go down here. I'm going to change the color of that line because this is going to get real complicated real fast. So let's get a nice blue color. Everybody likes blue, right? Right? Or is that just sexist? I don't know. Okay, so off we go, and then what we want now is we want a wee dotted line, because when you see a ray of light strike an object, it automatically generates a normal. Okay, you should be automatically thinking that. Okay, put some arrows in this because it's not light unless it's got arrows. And then, as we said before, we should measure this angle round. So here's my angle of incidence, angle of reflection somewhere like that, I would think. They're not using a protractor, and for a good reason. We'll see in a minute. Right, and that's going to go down there somewhere, like that, and a ray of light now. Okay, cool. Now, if we stick in the way a person's eyeball, so this is going to be a quick drawing of an eyeball. Okay, so that's somebody's eye there. That's terrible. It's not going to get any better, I'm afraid, but you know, shade that in. There you go, front of an eyeball, eyelashes up there. Little bottom lashes, yeah, looking lovely. This person needs to go and see like somebody seriously. Okay, well then the eye receives two rays of light coming into it, and the human eyeball has no concept whatsoever of the idea that light can bounce off stuff and reflect. Okay, your eye is conditioned through evolutionary processes, or whatever you want to say, whatever way you want to think about it, to think that light comes from in a straight line positions. Okay, so what your brain does is it takes this light and it goes, well, this ray of light is coming along this line, so it must have come from back here somewhere, because light travels in straight lines. Which is remarkably clever of your eye. Well done. It then sees this one and goes, well, this one is also coming from some straight line position way back, so it's like here somewhere. Okay, now because your brain is getting the same piece of information, because this light is coming from the same point, it will use this to go track back, and then will construct a picture in your brain of what it thinks is there. And very important you understand that what you see is not what actually goes into your eye, it's what your brain understands by what goes into your eye. So over here is where your brain puts the spot that should be over there. And that's why you see stuff inside a mirror. There clearly isn't anything there. It's an optical illusion created by your brain because of the assumption that it thinks that light travels in straight lines. Now you'll notice a couple of things about the diagram I did. First of all, the lines that travel backwards are dotted. Okay, they're dotted lines because they're not really light. They're not actual bits of light, they're what your brain thinks is true. You'll also notice there are no arrows on this, okay, because imaginary light can't go in a direction. So you don't bother with arrows on these, you do bother with the arrows that come out with the real light. That tells you what's actually happening here. Okay, now our little object is not bad, but if I was to draw a line from here across to this one, the way I've drawn it, my image here, my pretend one, is a little bit higher up than my original. Okay, and let's just take a little measurement tool. Is it the same distance into the mirror as it is? There's the distance it is in front of the mirror, and the distance behind the mirror is pretty much bang on. Actually, I've done a good job there. I've done a pretty good job. In reality, what you should have is you should have the ray of, or the little object being exactly the same height, exactly the same position behind the mirror as it is in reality. Okay, it should be the same distance into the mirror as the object is outside. If you don't believe me, go and set a tape measure in front of your reflection. Okay, and you stand at one point in the tape measure, your reflection is standing at the same point. So it's the same distance into the mirror as it is outside of it. And we can cheat a little bit in our construction of our diagram. I'm going to show you how to do that now. If you're ever asked in an exam to draw a diagram to show how you form an object in a mirror, then you cheat. Simple as that. What you do is you get your ruler out, you measure to there. You know that it should be the same distance behind the mirror as it is in front of it. So get your ruler out and put it where it should be. There you go. And we're going to work it from here. Alright? So take out all these lines, and all you need to do is realize, okay, well, what's going to happen? my brain is going to think that the rays of light come straight from this one out to this one. Okay, so we draw a line out along here. Okay, but of course we can't make it solid the whole way along because this side of the mirror is imaginary. So you drew this end dotted. And what I'm going to do is I'm going to shorten this one. Okay, so we've got a dotted line like that, which is magnificent. And then we do another one. Okay, so we grab another line, and it has to be diverging from there. So we'll do the dotty bit first. And then we'll do a solid line over the top of that. That's lovely. Look at that. Okay, so that's what your brain thinks is going on. Oh, wrong one. Shorten that. So your brain thinks that's happening. So now what we've got to do is we've then got to build up, right, well, what is actually happening. Well, what is actually happening is a ray of light is coming from out of there and hitting there and bouncing into my eye. And a ray of light is coming from out of there and hitting there and bouncing into my eye. And there we go. We've got the perfect diagram. All the angles here are right. And this is exactly as it should be. Now, we're not really cheating. We just happen to know what the answer is. And since we don't have a protractor, we're making the diagram as accurate as we can. Drawing a couple of normals, just make it look as if you've really done your due diligence. And you should always draw a normal. And make sure that you draw arrows onto every ray of light that you actually have going on. And that's how your eye positions an object in a mirror. Now, the object in the mirror has some properties. Okay, properties are just things about an object. So properties. Okay, so for a start, this object is virtual. It's not really there. Now we need to be able to explain what virtual is, especially if you're doing triple award. This has been asked several times. Like, what is a virtual image? Okay, and it is no actual rays pass through the object or through the image. Okay, and this idea here, pass through, these are the key words. Okay, rather than saying no actual rays are there, it's no actual rays pass through the image. We've got an image here, but no actual rays of light go through it. Okay, it is the same distance into the mirror as the object is in front. Okay, I'll put some little dashes here because we're going to double lines for things. So that's that. So it's virtual. It's the same distance into the mirror. It is upright. The person you see in the mirror, if you're standing up, is the same way up as you are. But it is called laterally inverted. If you raise your left hand, the little mirror you raises the right. So you're laterally backwards. You're side to side backwards rather than up and down backwards. Okay, so laterally inverted that way. Virtual, same distance, laterally inverted, and you should be the same size as the object. Now you might think that is not true. If you look at yourself in the mirror, you look kind of smaller. But that's because you are actually smaller. Because this is small, this is far away. Okay, that you are further away as you step backwards from the mirror, and as a result, you look smaller. But if you stand right up next to the mirror, you are the same size. Okay, Father Dougal had difficulties with that in Father Ted, and you're all too young for that, so let's move on. Okay, with 12 minutes left, then we're going to take a look at refraction. And refraction basically falls into, basically a table. If you learn this, you don't go wrong with refraction. Okay, so we have change of material as our title, and we'll ignore the terrible table tool in this. Notebook's great, but it's terrible at this. Okay, change of material, speed, and direction. All right. So if we go from a change of material, so we say that something is that you're going from a more dense material to a less dense material. Now, being clear, you still have to be able to actually go through this material. It still has to be a transparent material. So you're going from something like glass into water. Like, both are see-through, but glass is denser. More dense. Okay. Then going from a more dense material to a less dense material, you're going to speed up as light. Okay. There are less kind of particles per unit volume getting in your way to slow you down. So you're going to speed up. And your direction is going to, what you're going to do is you're going to change direction away from the normal. Okay, now think about it as in, if you're speeding up, you're trying to get away from something. I speed up to get away. I speed up to get away. Okay, from a less dense material to a more dense material, you got to slow down. Again, that sort of makes sense. And and the direction change is going to be different. It's going to be closer to the normal. Okay, think I'm slowing down the corridor to make sure that that person that I kind of really quite like but don't want to tell them that I quite like ends up getting closer to me, so I can awkwardly try and talk to them in some way, or just me, maybe just me. Okay, so with this in mind, we're going to keep this little table somewhere handy. We may not be able to, there we go, we'll keep that nice and small, and over here we're going to take a look at what happens when a ray of light travels into a glass block. Okay, so kind of important that we label what this is. This is glass here, and this is air out here. So I'm hoping that at GCSE physics you understand that glass is more dense than air, and therefore light that's coming from air into glass is going to be going from a more dense material to a less dense material. Okay, so we see a ray of light that's striking an object. Our immediate reflex should be to draw normal. Okay, so that is a line that's at 90 degrees to the surface of the object you actually strike. In this case, though, we're going to draw normal through the material, like this. Okay, still at 90 degrees on both sides, but we're not just dealing with reflection. Now, importantly, there will be reflection. Okay, that will happen, but we're not interested in that. There will be a little bit of reflection. There's reflection when light hits most things. All right, but what we want to do here is we want to see what happens. Okay, so we're going from a less dense material to a more dense material. Our speed is going to slow down. Kind of hard to show that on a picture, so we're going to ignore that. And we're going to go closer to the normal. Now, closer is a comparative term. That means you have to be going closer than something. Okay, so what you're going closer than is you're going closer than what it was going to do. The light travels in straight lines, so it was going to go straight on. And we now need to get closer to the normal. So if I try to swing this way, I'm going further from the normal. So I can't go that way, so therefore I'm going to go this way. I just need to get a little bit closer to the normal. Now notice something that happens in exams a lot is that you get this kind of happening. You're like, oh, it's closer to the normal. And it is. But in order to get here, over on this left-hand side of the normal, I would have to go closer, 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 but now further away. Okay, so I've not just gone closer to the normal. So I haven't followed my rule there. So anywhere in here will do. There's no requirement at GCSE stage to be able to do the calculation for that. We'll save that for you for next year in AS physics. All right, that's half the question done. But again, we see a ray of light striking an object. Immediate reflex, draw normal. So let's get our 90-degree line in here. And let's figure out what happens. Notice I drew the normal before figuring anything out. I'm going from glass to air. That is from more dense to less dense. So I'm going to speed up and bend away from the normal. Bend's the wrong word. Change direction's a better word, but you know, we're going to allow bend, I suppose. So again, it's we're going to bend further away from the normal, so we're going to get further than something. So we want it to go straight on, but we now need to get further from the normal. So I can't go this way at all because that involves getting closer to the normal. So over here is where I'm going to head. Now again, you don't have to be overly accurate with it, but we can be a bit pedantic that because this side and this side are parallel to each other, then the amount that you're going to bend going into the glass probably should be the same as the amount you're going to bend going out of the glass into air. So this incoming ray and this outgoing ray should sort of be parallel. That's the best, you know, like, don't worry too much about it. Examiners are pretty lenient as far as that. Okay, hopefully that's refraction sorted out for you. The problem is not rectangular glass blocks. Usually people are pretty good with that. The real problem comes when you start doing like random shapes. So let's try this. Okay, and we'll bring our little table across because we'll see if we can mess with your head a little bit here. Okay, so in this one actually I'm going to have my ray of light coming in like this. Okay, and let's say that I'm going from water this time into glass. Okay, because I don't want a whole pile of people having a complete and utter freak out that after what happens with this, be like, total internal reflection takes place. We're not doing that tonight. We'll deal with total internal reflection another time. Okay, so I see a ray of light striking an object. So I need to draw normal. And I'm going to draw my normal red because otherwise you'll not see it. Because my ray of light is coming in along the normal. And that's problem one. Okay, because we've got change in material. We're going from water to glass, so we're going less dense to more dense, let's say. So we're going to slow down and we're going to get closer to the normal. Now the problem is that 0 degrees is kind of about as close as it gets. Right, so getting closer than 0 is sort of difficult and therefore doesn't happen. Any ray of light that comes in along the normal, be this in reflection or refraction, doesn't actually change its direction at all. It just continues to travel straight on. It's kind of a special case here. Now this is the bit here. I want you to take a look at your screen before I do anything. We see a ray of light striking an object. We need to draw normal. Where would you draw the normal? Because what you need to do is you need to make it in such a way that it starts, we'll shorten this one a bit, it starts where the ray of light hits the object and it forms 90 degrees to the surface of the object. So it should look like that, and I'm going to extend it into both sides because we don't know what's going to happen to our ray of light. Okay, and that's what we're after here. That's the normal for a slanty side. Turn your page sideways. There's nothing special about up and down on your page. Okay, so we're going from glass this time into water. So we're going more dense to less dense. Going to speed up and move away from the normal. So I wanted to travel straight on, but now I'm going to have to travel further away from the normal. So that's out. I can't go this way because that's getting closer. So away from the normal is down this way. Okay, and that's refraction in a different angle. Okay, so 3 minutes left to do dispersion. Dispersion is sort of a special case of refraction, but when you've got a triangular prism, and that's basically a triangular glass block. Ray of light comes in, like this. And there's to be sound effect there, you know, spare no expense. Draw normal, which should look something like this. Don't know why I went all accenty there. Now we're going from out here. We've got air. We should label these things. So we have air and glass. And I'll bring my little table with me just in case we're not familiar with this. Grab that and set it up in the corner here. That'll do all right up there. Okay, going from air into glass, then we should be slowing down and getting closer to the normal. So we go slow down, get closer to the normal, hit there, I suppose. Okay, draw myself another normal. So grab this dotted line and spin it around. So we start our line where it hits, form 90 degrees, just like that. Extend. And you do it that way as well. And then we speed up on the way out and we get further from the normal, so down this way. Alright, and that's not very interesting, it's just what happened like the last time. Except that now we understand that, well, this is random. I just picked like a little bit of an angle. Like I could have very, very, very easily drawn this, that instead of slowing down and bending towards normal like this, I could have bent towards normal like this. I could have just done a bit more bending. Okay, draw myself a different normal out here. And because I'd bent more with the first one, I suppose I'm going to do the same with the second one, so bend a wee bit more and get out here. Okay, and what's to stop me doing that? And in our current model, nothing. But in reality, the amount that light bends on the way in through glass, as it's coming from air into glass and then back out again, the amount that it bends actually depends on its color. Okay, it's wavelength and frequency dependent. Okay, so it depends on the frequency of the light. It depends on the color of the light. Where some colors are bent very little and some colors are bent an awful lot. You don't notice this in the rectangular glass block problem because the ray bends first one way and then bends the other way on the way out, so it all kind of recombines back into a nice beam again. But if I have white light being sent into a prism, the interesting thing is that white light's not a color, it's just made up of lots of different colors. We see white because it's a mixture of 7 colors. And those 7 colors separate themselves out depending on how much they bend by. And they separate themselves out in order, where red is bent the least, And violet light, okay, that's a purple for all the boys that are watching. It's kind of purpley color because we have no idea what violet is. It's what your mum calls purple. Violet light is bent the most. Violet is very refracted. Okay, or violet is very bent. So violet, V for violet, V for very bent. Okay, and there's some jokes about that, but not safe for this channel. And in between we have all the colours of the spectrum, which is red, orange, yellow, green, blue, and indigo, which is also purple but a different purple. And that's because this was discovered by Isaac Newton, and Isaac Newton had a real thing about the number 7. Thought it was very, very important that things were like in sevens. So instead of calling this indigo and violet purple, light purple and dark purple, he separated purple into indigo and violet, and we're stuck with it because Newton was awesome. Nothing we can do about that, and you need to be able to remember that order. Now, back in the day, people used to remember that by saying Richard of York gave battle in vain, and that required you to have some degree of knowledge of history. If anybody had any idea whatsoever of who Richard of York was and where he gave battle and why he did so in vain, I'd be very, very impressed. It's not generally part of World War II history that you do at GCSE. So the somewhat easier way to remember it is to remember a person's name, which is Roy G. Biv. It's sufficiently terrible that it actually works. And my personal preference is to imagine an unpleasant character, because I know, maybe it's a hangover from watching Back to the Future that Biv sounds like Biff, and therefore this person had to be unpleasant. Okay, so I imagine, little fella, little cap on, like those Burberry caps. Nothing against Burberry, but you know the people I'm talking about. Little cigarette in his mouth. Little beady eye up there, it's up to no good. Right, vaping away like nobody's business. There he goes. Right, Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Where violet is very bent, red is least bent. The most common exam mistake here is when you're asked to draw this, people draw like one bent ray that then splits into 7. The splitting actually starts in here. Make sure that you split the light up when you're inside this part here. You should have 7 separate lines that are quite close together, and then those 7 separate lines separate out even further with their own individual normals and bending points there. There's a question like that on the little worksheet that's linked in the description below, but we're 3 minutes over time, so I am going to bow out for the evening, and thank you all very, very much for coming along tonight. Please leave a like, hit subscribe, share with your friends, because it makes me happy seeing people on a Wednesday night wanting to do physics. So all that remains for me to say is, ladies and gentlemen, good night, and physics rocks. It's true.